Another example, which should be somewhat familiar since it was on the quiz, is this one where we have a function that'll take an equation that is commonly used in the study of faulting. And here we have a view of a fault like this San Andreas fault, some plate boundary fault. It's locked near the surface to some depth d, so that's what breaks when there's earthquakes, but deep slip due to steady plate tectonic loading occurs below that. And so as we deform this plate, we can see that the surface displacements we might measure from GPS will vary. And so this equation just says the displacements in the x direction, which is parallel to the fault, as a function as we move away from the fault, which is the y direction, are a function of the deep displacement rate u dot over pi times a tan of that distance away from the fault y divided by the depth of locking d. So let's look at how we might implement this in MATLAB. So go back here to MATLAB, and I've got a script here started. So you see I have function u dot xy equals deep slip, which will be the name of my function, and then my arguments are the u dot, which is the deep slip rate, y, which will be a vector of positions, and then d, which will be our locking depth. And so then here's the equation in MATLAB speak, as it were. And notice, very importantly, I'm using the dot, star, and dot slash for the math. Now I've also got my plotter function. I'm going to need that, so let's just remember it. So let's say here we need to first set our variables, and so let's say u dot equals, now these need to be all in the same units, so let's do it in meters. So let's say, I know that the San Andreas fault moves about 35 millimeters a year, so this is in meters if it's 0.035 per year. And then d is going to be the depth of locking, which would be in meters again, 10,000 meters. So that's how thick the brittle crust is there. Depth of locking in meters. And then y is going to be our positions relative to the fault. So we need to use our range. So let's do minus, let's say, 50,000, and we'll compute it every kilometer. So we'll have 100 calculations, 50,000. Okay, I'm going to not show that one. So that should be my arguments. I'm just going to go grab our function here so I can get it correct. So u dot yd, okay, that looks good. I'm going to suspend this because we don't want to necessarily see all those values coming out. And so once we have that, then we want to be able to plot it. So let's grab our plotter function that we made in an earlier example. And so I'm inside this script, and so I can say plot result. I should go ahead and say up here do calculation. So here our x value, which is actually the distance along the fault, is going to be, or perpendicular to fault is the y, so that's what we want along that basal axis. And then the u dot xy is our dependent variable. That's what's going to go on the vertical axis. And then my title, we can say deep slip calculation. And then my x label will be distance from fault in meters. and then the y-axis is going to be displacement rate in meters per year. And then my plot style, let's use our blue line again. So we'll save it, go back to our command window. Let's do a CLC so we can keep it clean there. And we just run it deep slip script. Okay, so it doesn't like the capital P of pi, so let's go back and change. That's going to be inside our function. We'll do it here, lowercase p. Save. Now we don't have to save the script because it's just calls the function when it needs it. And we've updated our function, so let's try that again. And we got all of the values we calculated, and there's the curve. And so what this shows is that at the fault things are fixed, and at the edges we're sort of slowly displacing the crust, and this is, so we're loading up. The reason that gradient's there is that the fault is locked, and then it could snap in the future, and that's called elastic rebound, and then this part would snap to here and that would snap there. So you could change it. The beauty of this approach is we could say, well, what if the we wanted to broaden this? We went out to 80,000 meters on either side to kind of see the broader effect. So we just say save, go back to MATLAB, and run it, and then look at our figure. It's wider, so we're seeing that once you get pretty far away from the fault, it looks like it's steady block motion. So that's the beauty of this approach, is we can just change our main variables up here. We don't have to change our functions at all, and arguments are updated. And so it's a real simple programming approach.